In this video, we are going to talk about the concept of force fields in molecular dynamics. Interactions in molecular dynamics can be described using the concept of force field. The force field is represented by a potential energy V of the system, which is function of the position of the atoms R. This potential energy is composed by the sum of two terms, a bonded part and a non-bonded part. The bonded part of the potential energy represents the interactions between atoms in the same molecule connected by one or more bonds, whereas the non-bonded part of the interaction energy describes the van der Waals interaction between atoms and the electrostatic interactions between atoms. We assume that the bonded part of the potential is composed by the sum of four different terms: the stretching of bonds between two atoms, the variation of the angle, the potential function which describes the variation of the angle between three atoms, the potential function which describes the variation of the torsional angle between four atoms, and the potential function which describes a particular quantity called improper torsion angle. The non-bonded part of the potential instead are described as the sum of two main terms. The first describes the van der Waals interaction, and it is used modeled using a Lennard-Jones type potential or Buckingham potential, and the electrostatic part of the non-bonded interactions described using the Coulomb potential. But why we call these functions, this interaction, a force field? Because from the knowledge of the potential function V of R, we can obtain the force for each atom in each position x, y, z. And we do that by taking the derivative of the potential, the negative of the derivative of the potential with respect to the position, using this operator, which is called the gradient operator. So just an example, let's derive the bond stretching force just in the x direction from the bond stretching potential, which I'm reporting here. So if we take the derivative with respect x for this potential, we obtain the force in the x direction between two atoms connected by this potential. We can check that this formulation is correct by taking the derivative, by calculating the force on the opposite atom belonging to the same bond. We obtain that this force is exactly the opposite as the one that I calculated for atom I. And the Newton third law is preserved. So let's start our discussion of the interactions between atoms by first looking at the bonded part of the potential. As I said, the bonded part of the potential is composed by four different terms, which represents the four different interactions between atoms connected into a molecules, as it is reported in the figure here. So the first term of this sum is the terms that model the stretch between two atoms connected by a bond. So in this case, this atom and this atom connected through this bond. It is an harmonic potential, which depends on the equilibrium position R subscript 0 and an energy constant K subscript B. Do not confuse this K subscript B in this case with the Boltzmann constant. This is not the Boltzmann constant. It is another quantity. It just happened to have the same symbol. The second term in the sum is the term that describes the variation of the angle between three atoms. So here this could be, for example, a water molecule. We have hydrogen, oxygen, hydrogen, and this term describes the variation of the angle in a water molecule. It is modeled again with an harmonic potential, which depends on the equilibrium angle, theta subscript 0, and another energy constant. The fourth term of the sum is the torsional potential, which describes now the interactions between four atoms. The torsional potential can be better visualized using this picture here on the right side of the slide. So if we have four atoms, we can build the plane in which three atoms lie. For example, if we consider these atoms, and this atom, the plane described by these three atoms is this red plane. If we consider instead this atom here, this atom here, and this atom here, the plane described by this atom is the green plane here. Now, the angle between these two planes represents the torsional angle of these four atoms. The torsional angle represents the rotation along one bond of four atoms. If you consider these four atoms here, you can see that these two external atoms, this one and this one, can rotate along this bond. The amount of rotation gives the torsional angle. The torsional potential is described using this sum of cosines, and the reason is reported, can be observed in this picture here, is because this torsional angle, torsional potential has different minimum, and this functional shape describes the rotation along the different the different torsional angles. The last term of the sum is the improper torsion, and it is again an angle given by four atoms, but in this case it is used to keep some specific shape of the molecule. Most importantly, when we want to keep the four angle planar. If we don't want that, let's think about a benzene ring. In the benzene ring, all the six atoms have to remain planar. In this case, we use the improper dihedral to keep the configuration of the atom in the same plane. Let's start our discussion of the non-bonded part of the potential by considering the Lennard-Jones potential. Non-bonded interactions had to describe three different behavior of the interactions between atoms: the repulsion, the dispersion terms defined by the van der Waals interactions, and the Coulomb term. The Lennard-Jones potential describes the repulsion and dispersion interactions between atoms. The Lennard-Jones functional shape is reported here, and as you can see, depends on this R subscript ij, which means that depends between the distance between two atoms. That means that the Lennard-Jones potential is a pairwise potential, and it also depends on these two parameters: epsilon ij, that means that has unit of energy and represents the strength of the Lennard-Jones potential, and sigma ij, which has units of length and describes the division of Lennard-Jones potential between the repulsion part of the potential and attractive part of the potential. The Lennard-Jones potential is usually called the 12-6 potential because it depends on the inverse of the distance between two atoms to the power of 12 and to the power of 6. The functional shape of the Lennard-Jones potential is reported here, and from here we can see why I was talking about regions of the Lennard-Jones potential. The first part of the Lennard-Jones potential, the one that goes from V equal to 0 and plus infinity, is the first part of Lennard-Jones potential, which describes the interactions between two atoms which are very close together. As you can see, when the closer the two atoms get, the higher is the potential. This part of the Lennard-Jones potential describes the fact that two atoms cannot interpenetrate. The closer they get, the stronger they get repelled from each other. The Lennard-Jones potential, as I said, becomes zero at distance sigma when r is equal to sigma. After this distance, we enter into the attractive region of the potential, where the potential is negative. The minimum of the Lennard-Jones potential is obtained at distance 2 to the power of 1 over 6 sigma, and the height of this well is actually equal to 2 epsilon. We can expect that atoms will spend much of their time going back and forth into this potential well. For values of r bigger than the minimum, the Lennard-Jones potential goes to zero. However, it does never reach zero in a finite distance r, but it approaches zero asymptotically. That means that the Lennard-Jones potential tends to zero when r goes to plus infinity, but is never zero for a finite distance of r. This fact is going to be turns out to be really important for molecular dynamics calculation and will be described in more detail in a later slide. So the Lennard-Jones potential is not the only the only potential that can be used for to model the van der Waals interactions between atoms. One of the few of the other most used potential are the Buckingham potential, which is reported here, and the Weeks-Chandler-Anderson potential. So with respect to the WCA potential, you can see that this is purely repulsive potential because it starts from plus infinity when r approaches 0 and then decreases towards 0. So there is no attractive part. Instead, the Buckingham potential is a potential which is that gives interactions more realistic with respect to the pure Lennard-Jones potential, and in fact, you can see that it has a part of this Buckingham potential is similar to Lennard-Jones potential, but instead of having a part which goes to 0 as r to the power of 12, you have this exponential. The problem with the Buckingham potential is that it is much more expensive to compute, and molecular dynamics simulation people usually prefers the Lennard-Jones potential because it is much cheaper to be computed. I ask you to think about what happens when this potential when r goes to 0, and try to think what could be the difference with respect to the pure Lennard-Jones potential. As we said in the previous slides, Lennard-Jones potentials depends on two different parameters, epsilon and sigma, which are specific for the specific atoms that you are considering. If you are considering, for example, argon, you will have a specific value of epsilon and sigma for the argon atoms. However, in a real system, you have a mix different molecules, different elements. Uh, you can describe the interactions using the Lennard-Jones potential between these different atoms? Should you define different sigma and epsilon? The answer is yes. You should have different sigma and epsilon describing the interaction between different atoms. However, the good news is that you can derive the new value of sigma and epsilon directly from the one that you already have, the one for the pure system, the system composed by an atom of the same type. The way to obtain the new sigma and epsilon for your new system are called collectively the mixing rules, because they are rules that explain how to mix sigmas and epsilons between different systems. There are different type of mixing rules for Lennard-Jones potential, which are also used for the WCA potential that we just saw. One set of rules is the Lorentz-Berthelot rules, and one set of rules is the geometric rules. Basically, these rules says that you can obtain the new epsilon and new sigma as a geometric mean or an arithmetic mean. There are similar set of rules for the Buckingham potential, which are called, of course, Buckingham rules. That describes how to mix different A, different B, and different C coming from different type of atoms. The other potential included in the non-bounded part of the interactions is the Coulomb potential. The Coulomb potential, as you may recall, describes the interaction between two charges. And in this case, it describes the interaction between partial charges located on each atom. When the two charges have opposite sign, the Coulomb potential is attractive. So it's shown here. Instead, when the two charges have the same sign, the Coulomb potential is repulsive. In molecular dynamics, differently from quantum mechanics, each atom has a partial charge. It's called partials because it's given in percentage of the fundamental charge. This charge does not vary during the simulation. It's fixed during the simulations, and therefore this Coulomb potential is not going to this Qi and Qj for two specific atoms are not going to change during the simulation, differently from what usually happen with quantum mechanical calculation. Non-bonded interactions have a range that spans from 0 to plus infinity. That means that in a molecular dynamics simulation, we should consider all the possible pairs of atoms and calculate the interaction between them. However, in order to speed up the calculations, what we practically do in an MD simulation is to cut the potential at some finite distance that we call the cutoff. We assume that the new potential is the same as the one we were originally considering, for example, the Lennard-Jones or the Coulomb interaction potential, up to the cutoff distance. And it becomes zero for distances larger than the cutoff. That means that in a simulation we can exclude all the atoms, all the interactions that have a range larger than the cutoff. However, using the cutoff introduces some problems, some instabilities in our simulations. Since we are cutting the potential, we are transforming a continuous function with continuous derivative in a discontinuous function. This discontinuity in the derivatives, that means in the force, can create some problem in our simulation and also lead some non-physical results. So we cannot just cut the potential at a finite distance, but we have to find a way to take care of this discontinuity introduced. For van der Waals interactions that are modeled by the Lennard-Jones potential, uh, this is a much simpler task because the Lennard-Jones potential falls off very quickly as r to the power of minus 6 or r to the power of minus 12. That means that the potential approaches zero very quickly. We are going to see in the next slide how this is performed using switching function. For the Coulomb potential instead, the situation is much more complicated because the Coulomb potential decays only as r to the power of minus 1. That means that we need a very large cutoff to avoid this discontinuity of the force. And even in that case, we are not sure that the discontinuity is not going to have an impact in our system. In the picture here is represented the calculation of electrostatic interaction in a quartz crystal, and it shows you the red line with the white dots, the variation of the electrostatic energy with different cutoffs. You can see that the variation you have a very big variation of the electrostatic energy depending on the position of the cutoff, and this of course is not a physical behavior, and we don't want to have that in our system. For Coulomb interactions, we use different models to treat this problem, which are much more advanced. We are not going to consider them, but just to give you a few names, I'm talking about Ewald summation or particle mesh Ewald and others. So now, how can we consider? Well, how can we model the cutoff in the Lennard-Jones potential to avoid the discontinuity in the potential? We do that by switching the function or using switching functions. In one version of this treating of the cutoff, we are switching the entire Lennard-Jones potential to be zero at the cutoff. So we are basically taking the original Lennard-Jones potential, which is here represented by the solid line, and this one, and we are shifting this Lennard-Jones potential in order to have at the cutoff here the potential equal to zero. So now we can safely take the potential equal to zero for distances larger than the cutoff because we don't have any more we don't have a discontinuity anymore. In the second version, we are applying an interpolation from a finite distance here, which it is usually called an inner cutoff, up to the cutoff. So what we are doing here is, instead of considering the original Lennard-Jones function, we are interpolating with some polynomial up to zero. So the new cutoff, the new modified Lennard-Jones potential is equal to exact the same Lennard-Jones potential up to the inner cutoff here, and is different for the distance included between the inner cutoff and the cutoff, which is this value here. For values larger than the cutoff, the Lennard-Jones potential now is assumed to be 0. In the description of the force field that we encountered today, we saw that there are lots of parameters defining this force field, lots of parameters that needs to be prescribed in advance. For example, Lennard-Jones potential depends on epsilon and sigma, the bond stretching force field potential depends on the energy constant K subscript R and equilibrium distance R subscript 0. Where do we actually take these parameters? Where do these parameters come from? For bonds and angle, these parameters are usually taken from X-ray data. The values of the force constant instead are derived by fitting experimental vibrational frequency data. For the dihedral instead, there are two approaches, both involving ab initio methods. The first is if we want to obtain the dihedral angle for a specific part of a specific molecule, we can use the ab initio calculations to optimize the dihedral potential for a model molecule containing that angle. Or the second method is to if that dihedral angle involving four atoms appears in different molecules, in different similar molecules. For example, let's think about amino acids. We optimize the dihedral parameters to best describe a large number of different molecules. The van der Waals interaction potentials can be obtained by considering again quantum chemical calculations, or they can be fitted to reproduce some experimental data. For example, sigma and epsilon are adjusted to empirically match the experimental density and enthalpy of vaporization of the different substances that we are simulating. The partial charges instead that enters into the Coulomb potential are obtaining using ab initio calculation, optimizing the geometry of the molecule. We optimize the partial charges, which gives which reproduce the exact geometry of the molecule. One problem with using this way to obtain the parameters is that if the molecules has different multiple low energy conformation, in this case finding the optimal sets of value which reproduce the observed geometries is a little bit more complicated. So just a couple of words about the most known force fields. MM2, developed for conformation analysis, Amber, Charms, and Gromos, which were developed mainly for biological macromolecules, and OPLS, which was developed for was optimized to fit experimental properties of liquids.